Hey, this is Steven from Steven's Classic Garage, and welcome to another one of my analysis videos. I think this is kind of stepping away from where the channel used to be, but I mean, it's basically where my skills lie as used to be a mechanical engineer student. Now I'm graduated, so I have my diploma, I believe it's downstairs. Or actually, it's over here. Yeah, it is downstairs. Downstairs in mechanical engineering from a local university, and so it's where my skills and my teachings lie. So I wanted to kind of add how we could use that to help you guys, help you and me better understand some of these changes that we make to our cars and how they affect the car, and how we could explain what happens and how to increase power and increase drivability, increase comfort, etc., etc. And as you know, mechanical and automotive share a very, very close bond. Usually, mechanical engineers can be in the automotive. In some schools, you have mechanical engineers that specialize in automotive. So usually they can go into automotive if they want to. Very, very easy transfer over because a lot of the teachings are very prevalent. So aerodynamics is also in mechanical. Usually it's aerospace is more focused around that, but aerodynamics is also a focus there. General mechanics, which are like suspension, engines, which are cycles, thermal cycles, heating, cooling, which are HVAC cycles, or radiators, or heat exchangers is another thing. That's actually what my emphasis was. Originally, I wanted to do mechatronics. I wasn't able to do that because I was missing a class, so I took thermal. So I actually have a thermal emphasis from university. So basically, the stuff that we're going to talk about right now is kind of where I have my background, and in my day job, that's also what I do, is I work in thermal. But electrical and those other kinds of stuff are also in automotive. So, but the mechanical, which is what I'm into, is a big portion of automotive. So recently, I got a new toy for as an instrument for measuring, and instruments are very big for engineers and scientists, and we take a very big pride in having good instruments and taking good care of our instruments so that we could rely on them and do basically work and other things with them. Be able to make good decisions, good educated decisions based on our instruments. So I recently picked up what's called a IR camera. Now, what is IR? So IR is one of the three. We talked about this, I think, in another video if you watch that. But IR, infrared, or radiation. Radiation is one of the three forms of heat transfer. So you have conduction, convection, and radiation. Conduction is when two materials are touching. So, for example, put your two hands together or put one hand on the table. That is where two solids are touching each other. Or in the case of anything that's stationary. So when two stationary objects are touching each other, they are conducting heat or energy between each other. Heat is a form of energy, right? Number two is convection, which is when you have one stationary object and a moving fluid going over the stationary object. How does that heat transfer? How is that heat transfer affected because of the speed of the fluid going over it, the pressure, the humidity, etc. So that's convection. And the final one is radiation. Now, what radiation is actually a non-contact form of heat transfer. So what it is in space, that is actually one of the only ways that energy is transferred. So that is when there are no two objects touching each other and there is no fluid present. So, but it can be present when those other two are present. Generally, all three are present, or you'll have conduction and radiation present and no convection. For example, my day job, I work a lot using using vacuum chambers. So there is no air, there is no moving fluid. We suck all the moving fluid out. So it's basically like space in that case. So the only thing that's happening is that there are two things that are contacting each other, right? There is like something holding something else on the inside, and those two pieces are touching, two solids are touching. So that's conduction, and the second is radiation. So basically what radiation is basically from vibrations that are turned into waves, electromechanical waves, electromagnetic waves that come off the material that are transferred to you regardless of whether there is a fluid between that material or not. So all materials are doing this. For example, if you see at the store, you see these radiation lamps, where the lamps, they just get red hot. They are very hot to the touch, but there's no fan on that heater, so there's no convection. There's very little convection because it's not pulling the air across it, right? So basically, what you're feeling, and usually why it has like an umbrella on the back, is that it's reflecting that radiation towards you. Radiation cannot be seen, but it can be felt by the body. So, for example, one of the biggest examples of radiation is the sun. There is no fluid between us and the sun, between Earth and the sun, and there is no, well, I mean, there's air, right? But air doesn't go all the way up to the sun. Once air goes about 64 miles up, which is the Kármán line, which is from there on, it's classified as space. So 65 miles up from the Earth's surface is space, theoretically. So past that, the air gets exponentially thinner and thinner and thinner and thinner until there's barely any particles or any molecules of air remaining. So from us to the sun, there is 64 miles of air, and then there's pretty much nothing. There's very few particles, but not very few molecules that float around. But other than that, mostly vacuum. So very few particles very few molecules to transfer that energy. And energy through convection and conduction are transferred through molecules, right? Which are basically the molecules from internal energy are moving. And when they move, they could hit other molecules. And when they hit other molecules, they transfer the energy from themselves to the other molecules. But in space, there are no molecules to bump against each other because there's so few of them moving. There's so few of them in space. So there's no moving fluid and there's no solids. So the only way that we can feel the temperature from the sun, if you stand in the sun, is from radiation. And you can't see that radiation. The radiation is invisible to the human eye. The radiation actually lies in the infrared, which is a different type of spectrum that some cameras can't see, one of which is the camera that I now have. So I'll go over that in a second. But we see in the visible light spectrum, which is a very narrow spectrum. We have ultraviolet, you have IR, and then you have the smaller stuff, which is like radio waves, X waves, all those kinds of stuff. And you start to get into like nuclear type stuff, radiation, nuclear type radiation. So and then obviously they either get bigger in wavelength, and that's with wavelength with respect to these electromagnetic waves. So we could see a certain spectrum of electromagnetic waves, and that spectrum is broken up into all the colors of the rainbow, which is known as visible light. And then you have IR, which is basically a color gradient, I guess you could say, of I believe it's like from black to gray type thing. But it's different because you'll see some recordings from this piece of equipment, and that is obviously color coded by the software. It doesn't actually look like that in real life in the IR camera. The IR camera is just seeing, okay, this is the temperature of the material. I'm going to put this color on it relative to everything else. So that is basically what IR is, and it's very similar to if you have like a fire and you stand far away from the fire and you put your hand out, you could kind of feel the temperature of the fire on your hand, right? And even though you're far away, or maybe you're basically far away, but radiation is a form of basically it has to be line of sight. So you have to have line of sight between two objects. If you have something in between, they are radiated between each other, and then they are radiated between those to you. One second. A line of sight phenomenon where if you have something that goes in front of the sun and you cannot feel it. You cannot feel the sun. What will happen is whatever's in between you and the sun, that will take the radiation from the sun, and then it will radiate to you. So basically, everything is radiating. So right now, you're radiating heat, and your walls around your room are radiating heat as well. But the difference in temperature is so close because radiation is amplified by temperature, and the difference in temperature is so close that you don't really feel it, right? Because you guys are because you and the wall are very, very similar in temperature. While you compare to the sun is massively hotter than the human body is. So let's go ahead and look at. Does this have the equation in here? So this is the equation. How you figure out the power of radiation, and it's with this E, which is emissivity, which is basically how good is the body at radiating the energy. And this is just a constant that is determined by this equation by knowing all these unknowns. The Stefan-Boltzmann constant, and this is just a constant. It's just the same number that you put in there. The area, surface area, and the two temperatures. If you can measure the power output, and you know the two temperatures between the two bodies, and you know the area that they are seeing each other, the observed area, you could determine this the emissivity. So that varies between 0 and 1, right? I don't think you could ever get 0, and you can't always get 1. And then the closest you get to 1, we call that a black body, which is basically a perfect emitting a perfect radiation emitter, right? And also that can vary with temperature. I mean, with color. Also, black tends to be a better emitter of radiation compared to white. So, I believe I don't study radiation that much. We don't do too much of that at work. Here you can see this is from like skin damage. You could see using an IR camera. Skin damage, if you're burned, your skin doesn't radiate the same as the rest of your body, and it looks cold when the rest of your body's hot. So as you could tell from skin damage. And then that's the black body. So basically it varies here. Emissivity dimensions of unitless. It's basically from 0 to 1. It's unitless. And then Stefan-Boltzmann constant is this 5.670 times 10 to the negative 8 watt per meter squared Kelvin. And Kelvin is it's Celsius plus 273. It's an absolute measure of temperature. And then surface area of the object emitted. So basically, how much area is seeing from one side to another. So basically, that is the idea. So pretty much what this sensor does is it reads the power. It knows the power, and it knows its temperature. So it's going to guess the temperature. It's going to make an educated guess of what the temperature of the body that it's looking at. So by knowing this equation, we could actually measure non-contact. We could take an image using a camera and take an entire image and look at all the temperatures relative to each other without having any sort of probes touching those materials. So this is the one that I got. It was actually $400, which is very, very expensive. But I am going to be using it on my other small business. I do a lot of thermal stuff. I do a lot of plastic recycling stuff. And thermal's a big part of plastic recycling, thermoplastics. That's why they call it thermoplastics. They use a lot of heat to do that. So this is a 320 by 240 sensor. So it's a very, very old resolution sensor. You can see, but these IR sensors are very, very well built, and they have to be. They're very well calibrated, so they're a lot more precise than a standard regular sensor. Now, the exact difference, I'm not exactly sure, but you can look that up, what the difference between an IR sensor and a regular sensor. It's got 32 field of view and 9 hertz frame rate, so that basically determines how many frames per second. So this is basically 9 times per second, so pretty much 9 frames per second. Well, it says less than 9 hertz, so pretty much less than once. And hertz is times per second, so this is basically 9 frames per second, right? 1,800 feet detection distance, a focusable lens. So right here it has a iris that you could focus the lens, so you get the perfect, nice sharp edges. And it could detect between negative 400 Fahrenheit to 626 Fahrenheit. Waterproof with a case, photo and video, spot temperature, high-low temperature, threshold mode, 9 color palettes, audio and span level control, and adjustable emissivity, which again we mentioned is this number right here. So let's go ahead and show you guys some footage from this. So basically this is on the Rabbit, which I wanted to talk a little bit about more. So what I think I'll do is I'll break this video off into talking about what this is, and then we'll talk about how what we're going to get from this with the car. So this actually did record audio, but I muted it. Well, almost muted it all the way. There we go. Let's mute it all the way. There we go. So basically what you're seeing is you're seeing that 9 hertz, and then this you could actually see with the 320 by 240, which is a decently high resolution for an IR camera, actually one of the higher resolutions. We actually see what we're looking at here. So this is the radiator here. This is the radiator hose. This is the high pressure pump. Here are the lines to the injectors. You can see the lines are cold. And then here we have our spectrum here. So this is basically the IR is reading the power that it's emitting there, and it knows its temperature, and so it's going to guess the emitter's temperature. And basically the bigger the temperature delta between the two materials, the more precise the IR camera is. And of course it could measure up to 600 Fahrenheit, 630 Fahrenheit. So the further you get from room temperature, the better it is at distinguishing the temperature between not the accuracy of the actual temperature, but what that temperature is with respect to the rest of its room, right? Because basically this power here, let's say this power here is way more powerful than this one, so it's not going to get overpowered by its neighbors. So the bigger temperature delta that you have, the better off you are. You can see here I'm looking down into the radiator. You can actually see right here, this is the radiator fan blade here. And then here's one of the mounts, and then here's the motor. And so this was after I drove home here. And you'll see that it stops and it changes color, because what it's actually doing is it's adjusting this scale here. So it's adjusting the scale so that we have the hottest at the top and the coldest at the bottom. So whenever it sees another hotter temperature, it changes the whole scale and will adjust. So you can see now we're at 215. So basically it goes through and adjusts all the colors. And I found this really interesting. This is actually the hole for the transmission. Remember how I was missing that hole, that cover? Let me show you guys here. So if we look in here, pretty sure I open up the hood. So let's see if I can see it. Okay. Yeah, it's right there. You can sort of see it. Yeah, basically I'm missing an inspection cover on the transmission, and that's what you're seeing there, is the hole coming out of the transmission. So, and there you have the clutch, you have the flywheel, and those are friction surfaces, so there's a lot of heat coming out of that hole. And so that hole is showing really, really hot, showing upwards of 219 Fahrenheit. I think it's actually the hottest in the scene. But you see, even the transmission is pretty hot compared to some of the stuff that's around it, which is this lighter blue color. So basically, yeah, that's how this sensor is reading it, is that it's looking at the temperature in the scene, and it's mapping that hottest at the top, coldest on the bottom, and then using the entire visible light spectrum. You see every light is red, green, blue, yellow, or CYMK, cyan, and other stuff, but red, green, blue is the main colors, and it's shading all the way down, using as many colors as it can to differentiate. So I think that I'll split this off into one video talking about my new IR camera, and then we'll go into another, let's say 20-minute video or whatever, talking about what we are seeing here and what we can expand on.